Hey guys, it's been a while, so welcome back. We're going to be talking today about rotational motion, and we're going to focus on the constant angular acceleration. And just to start off, we want to remind you guys about what you've been doing this whole semester so you can compare it. So we've got our linear motion like we've been doing. So remember our displacements are delta x, your velocity is your v initial, v final, your linear acceleration is a, and then your mass force and momentum is our m, f, and p. So comparing it to our rotational motion now, we're going to start with this example right here. So you're going to imagine that you have a rigid object and it's rotating about a fixed axis, and you're going to consider an imaginary radial line, this thing right here, drawn from the axis of rotation to the edge of the object. So you'll start with this one, right? You've got your measurements of this angle right here as theta 1, and then when this object is turning in the direction of this arrow here, your line's going to end up over here. You've got yourself a new theta, a theta 2, right? So it's this area plus this right here. And this is how we measure how much your object's been rotated, right? And we call that your angular displacement. So it's going to be your change in theta. So for the units, you're going to want to use radians most of the time, and keep in mind that that is dimensionless. Sometimes you might see 1 revolution, which will be equal to 360 degrees, so all the way around, or 2 pi radians. So if you want to know how fast your object's been rotating, well, now we're going to use something called angular velocity, represented with this lowercase omega. And if you would like to know how fast your angular velocity is changing, well, you're going to be using angular acceleration, which you might see with different variables, but here we would be using alpha. So just like before, position, velocity, acceleration, same thing, just now in a rotational kinematics. And something we always want to consider when we are drawing any sort of diagram like that is our positive and negative directions. So generally when you have anything like this, counterclockwise is going to be your generally positive direction. So now we can start filling in our chart on the right-hand side. Again, angular displacement, we've got our delta theta, we've got our omega initial, omega final for angular velocity, and then our alpha for angular acceleration. So let's just define these mathematically real quick. We've got angular velocity with our change in theta over change in t for the average, and the same thing over here for our angular velocity on its own. And then again, just like a pattern, same thing down here for angular acceleration. And then for the period in our angular velocity, you guys are going to be using a t, which is the time for 1 whole revolution around the circle, and that will be t equals 2 pi over omega. And you guys have seen this before when you were doing linear displacement and stuff, with t equals 2 pi r over your vt, with your velocity sub t equaling your omega times r. So now you're going to want to be imagining that the angular velocity of any rotating object, it might be speeding up or slowing down at this constant rate, okay, alpha, then it follows that your initial and final values for the rotational kinematic variables will satisfy those constant angular acceleration equations, which are very, very similar to the equations for constant linear acceleration. So if you remember, we have these kinematic equations right here. You have seen them a million times, and they all have equivalent rotational motion equations that we're going to go through real quick here. So with our first one, this is our velocity at a certain time t, or after a certain time t, right? Originally it was vt is equal to v naught plus acceleration times time. Well, here you're just going to change these variables around. So now you've got angular velocity after time t, final here, equals your initial angular velocity plus your angular acceleration times time. So same thing, look at the patterns here. We got the second one here too. Exact same thing. This is your position after a time t, with just a reminder that your angular displacement is going to be your delta theta. And you can see the same thing here, except your omegas for your v's and your alphas for your acceleration. Third equation here, your final velocity, etc., etc. And then now we can put into this chart all of the equivalent equations that you once knew for linear motion and now you knew for rotational motion. So that's going to be it for this video. thank you guys very much for watching, and good luck in class.